All right. So we are in chapter 3, 3.9. So that right here is sort of where we're at. We are on our Friday, the 11th, and we are here. Homework 3 is due this weekend, as you guys are well aware. 3.9 and 3.10 is what we're working on. And so, 3.9, we are introducing a new concept. You won't use it super often. Okay, well, you'll use it every now and again. And what it is called is specific heats, C sub V and C sub P. And so, we can really quick. It's a heat transfer concept that maybe in 302 you'll talk about more. But for now, we're just going to introduce it. So it says several properties related to internal energy are important in thermodynamics. One of these is the property enthalpy, which we just talked about, right? Which is H is equal to U plus PV. So it's the internal energy of the fluid plus the work of the fluid, right? Is enthalpy. Two others, known as specific heats, are considered in this section. The specific heats, denoted CV and C sub P, are particularly useful in thermodynamic calculations involving the ideal gas model introduced in section 3.12, which is later, right? It says the intensive properties C sub V and C sub P are defined for pure, simple, compressible substances as partial derivatives of the functions U as a function of temperature and specific volume, and H as a function of temperature and pressure, okay? So, right here, C sub V, du dt with respect to v, and then dh dt with respect to p, right? Or the partial derivative. I'm saying d, but it's the partial derivative. And it says where the subscripts v and p denote, respectively, the variables held fixed during differentiation. Values for CV and C sub p can be obtained via statistical mechanics using spectroscopic measurements. We're not going to do that. They can also be determined macroscopically through exacting property measurements. Since U and H can be expressed in either on a unit mass basis or per mole, values of specific heats can be similarly expressed. SI units are kilojoules per kilogram Kelvin or kilojoules per kilomole Kelvin. These are the two ways that you can express H and U in SI units. And then English units is BTUs per pound. Oh, no, I'm talking about the CP. Sorry. CPs can be expressed in these units. So they will be kilojoules per kilogram Kelvin or kilojoules per kilomole Kelvin. And then we have BTUs per pound Rankine. So Rankine is the absolute unit of English units. And then BTUs per pound mole Rankine. Okay. And then it says the property K, called specific heat ratio, is simply the ratio of CP and C sub V. So right here. You may have to use K. I remember K is used for cold air standard of it's cold air standard analysis of engines, right? Like car engines. I think they usually give you K, and if they don't, you can find it. But we'll move on from that. So it says the properties C sub V and C sub P are referred to as specific heats or heat capacities because under certain special conditions, they can relate the temperature change of a system to the amount of energy added by heat transfer. However, it is generally preferable to think of C sub V and C sub P in terms of their definitions. Equations 3.8 and 3.9, and not with references, limited interpretation involving heat transfer. Okay? So, in general, C sub V is a function of V and T or P and T, and C sub P depends on both P and T or V and T. Man, there's a lot of ands here. Figure 3.9, so I think 3.9 is right here. Ooh, we went a little too far. Figure 3.9 shows how CP for water vapor varies as a function of temperature and pressure. The vapor phases of other substances exhibit similar behavior. Note that the figure gives variations of CP with temperature in the limit as pressure tends to zero. In this limit, CP increases with increasing temperature, which is the characteristic exhibited by other gases as well. All right. So, what does this all mean for you? Right? That's what you guys are probably wondering. What does it all mean to you? So what this means to you is that there are some questions where it is not... Okay, so it is probably possible to do it using the table way, but there are other questions where instead of giving you, let's say, a temperature and pressure at both stages, they'll give you a temperature at the beginning and a temperature at the end, right? And they'll simply ask, find the change in energy, right, or something like that. And so let me pull up what's this thing called, Epic Pen. So essentially what this is going to do is it's going to break into another equation, another form of how to find energy, right? And that is what we're looking for here. So essentially how these questions will more or less be done. This is a very popular method of this question, so I'll just go ahead and draw it out a little bit. So let's say we have a container here. I'll just draw out a little container, right? Let's say we have a container here. And let's say it's filled with water. Let's just say H2O, right? And let's say at the moment you drop in a metal bar, like we'll just call it a copper bar, right? Let's say you drop in a copper bar that was a temperature of like 1,000 Kelvin or so. I don't know. We're just throwing in numbers here, right? So then we draw in another bar here, right? You know, something like this, right? Another very simple bar, okay? So inside of here, this temperature is 1,000 Kelvin, right? And it will ask you very simply, it'll give you some properties about the water, and it'll give you the starting temperature of this bar, and it will ask you what is the final temperature of the bar, right? And so you guys will have to relate energy change, because remember, heat transfer works two directions, right? For example, the bar is going to give heat. It's giving heat to the water, right? Assuming the water is a lower temperature, right? It's giving heat to the water. But at the same time, the water essentially is taking the heat away, right? So essentially it kind of transfers in both directions, right? So water gets hotter, bar gets colder, you see? And so knowing some things about the water at both states before and after, you can find the initial temperature of the bar. And the problem is that this bar is usually just given as a temperature at the beginning. And if you guys notice, there are no tables in the back for copper bars, right? So we don't have any way of doing that. But if you guys recall what was just said in the previous part of this, it said that temperature changes using specific heats can be related. Basically, it can be a way to tell the change in energy of something. I think, where did they say it? It says, however, under special conditions, they relate the temperature change of a system to the amount of energy added by heat transfer. So they're about to show the equation. I'm going to guess. Maybe they will. I don't know. But this is something I did want to show. So where is it? Here it is. So table A22. So right here. So this right here is the table for specific heats in the back of your book. There are two of these. There's one for English, one for SI. This is the SI one. And so right here, you get the CP value of air at all of these temperatures, right? Nitrogen at all of these, right? And it gives you CP, CV, and K. And so you can use it for all of these different substances, right? I think it ends there, though. It gives you a bunch of gases, right? Generally speaking, what they will do is they will give you the specific heat for something that's not shown in here. Like in the question, let's say it was, that copper or whatever I was talking about. They will give you that, since it is not listed here. We can't possibly have a list of every CP known to man, so it will be here. Whatever you need will be here or given. But this is an important place to come, because just in case you ever need a CP of air, or a CP of nitrogen, or whatever, oxygen, you know that there is a table here that gives it at various temperatures in both English and SI units, okay? I just want to make sure that is clear. So, with that being said, we'll roll back. So right here, we're moving on to evaluating properties of solids and liquids. So how that last one is going to work is essentially that CP is that it will just be an addition to a question. It'll be something like using this. Basically, let's put it this way: you'll know if the question. This is like the test taking way. But if the question gives you a specific heat, you should probably know that you're going to have to use a specific heat, right? It's probably not. I don't think any of you would. I don't think you guys would have been fooled by that. You probably would know immediately you have to use it. But we're moving on to 310, and then we'll probably do a question involving a specific heat just to soak that in. So it says, evaluating properties of solids and liquids, or liquids and solids. Special methods often can be used to evaluate properties of liquids and solids. These methods provide simple yet accurate approximations that do not require exact compilations like the compressed liquid water tables. So if you guys remember a week or two ago, I said that the compressed liquid water tables, if you go to them, they are not really complete. Not that they're not complete, but they're essentially really difficult to use because they only show up for certain pressures, like really, really high pressures and really, like lower temperatures, right? And so the problem is that it's like here, look at this. It's 25 bar, 50. It makes these huge jumps from 150, and then we go up by another 50. And so essentially you can only use these pressures to really find where you're looking for. And so how we get around that is that we go back to the previous one, is that what it says is that you can approximate values using the liquid water or the liquid tables, right? The liquid value. And so it says these tables show that the specific volume and the specific internal energy changes very little with pressure at a fixed temperature. Because these values of V and U vary only gradually as pressure changes at fixed temperature, the following approximations are reasonable for many engineering calculations. So, really quickly, let's say you have a compressed liquid, right? A compressed liquid, and you have it at some temperature. You can say that specific volume, right? Specific volume of what you're looking for at a temperature and pressure is equal to the V sub F value at temperature T. Now, really carefully, you notice how it said temperature T here. And it says U, it's the same thing with U and H, right? But you notice how it says V sub F at temperature T, at this temperature. The reason why it says that is because this approximation only works for the temperature table in the book, okay? So if you have a saturated liquid value, right? If you have a saturated liquid value, or let's say it's compressed, like a super high compressed liquid, you can approximate it at the temperature instead of going to the compressed tables. That right there is basically what this is trying to say, okay? So so U and V and H and all of these values can be approximated at the temperature table. So I'm going to go to that really quickly to make sure that I'll find an example of this soon. But essentially here, if you know, let's say you know the temperature, right, of a certain fluid. Like let's say coming out of a process, the temperature is, let's say, 30 degrees, right? Let's say it's 30 degrees, but it's at high pressure still, right? Or it's at some pressure. You can say, okay, so I know it's compressed, but because if you keep the temperature the same, these things don't change. Not very much. So essentially what they are trying to say is that if you go to the saturated liquid value for specific volume at a fixed temperature, that value that I've circled over here, right here, doesn't change very much with pressure. So essentially we can kind of say this. We can at a fixed temperature, by the way. So we can kind of go, okay, it doesn't change very much. So we can say, all right, if we need to find it, we'll just use this value, right? Instead of having to interpolate whole new tables, right? Because let's say you have a pressure that isn't shown on this table, right? Let's say you have like 35 megapascals or something, right? It's not on the table. So how would you get it? That's where it becomes a problem, because if it's 35 megapascals and subcooled, if you go to the pressure table here, remember this table only tells you saturated values, right? It only tells you saturated values. So what you have to do is you have to find a temperature of the fluid and then look at that temperature in the temperature table to approximate the values, okay? So we'll get an example of this, and I'll try and make this a little more clear. But essentially, if you are going to find a saturated liquid, if you have a compressed liquid state, you can use this value, and I think it's this one, this value, to approximate your answer for all three of these, which is V. Yeah. So it's V sub F, U sub F, and H sub F. You can use these three values to just say it's close enough, right? Instead of trying to interpolate a whole new table and make new table entries, you'll have to just do that. And this is something that happens a lot. You will do this a lot in Thermo 1 and 2. You will do this exact process a lot. So I want to make sure that this is sort of clear. All right. Let me see if this is... Yeah, so they just tell you that this is the exact same process for H sub F. You can do the same thing, just like I said. Okay? All right, let me see. And not too important. All right, so we have incompressible substance model. Let me see if this is important. I don't think this is important. I don't think you do anything with this. Yeah, I'm not down for that. I don't think you do a whole lot there. All right. I think, let me see if this is useful. That's a good question or not. I might look at the lecture notes really fast to see if we have a good question. I don't know if he does or not. I know Dr. Matthias usually gives a question like that copper bar thing. He usually gives that on an exam, so that's if he wants to be to do it. But let me see if this is it. Let me see if he has a good example. We might do it. Lecture 9. Alright, okay, so let's see. 3.89. So I'll actually go to that really fast. Because I don't think... It said we had to do 3.9 and 3.10, so I'm not too worried about it. Let's go look at those and see if we can get an example in real quick. Alright. Sorry for this. I should have had that open at the beginning, but that's okay. 3.89. So let's see if this is it. So it says, as shown in figure 3.89, a system consists... Actually, since we're actually gonna do this, I think. So I'll just pull this one over here. All right, and I'll pull open a Paint 3D, and we'll do this really fast. Maybe fast though, we'll see. All right. So this right here is our question. Unfortunately, I made that really dumb. Of course, that was satisfying. All right, let's set this up. So up here. All right, so it says, as shown in figure 8.3.89, this is this right here. A system consists of a copper tank, okay, whose mass is 13 kilograms, 4 kilograms of liquid water, and an electrical resistor with negligible mass, okay? The system is insulated on its outer surface, so they've given us a little bit of information there. Initially, the temperature of the copper is 27 C, and the temperature of the water is 50 C. The electrical resistor transfers 100 kilojoules of energy to the system. Eventually, the system comes to equilibrium. Determine the final equilibrium temperature in degrees Celsius, okay? So this is like a very typical question that you would get using specific heats and using some temperature equations, right? So this is something you will see quite a bit of. So let's go ahead and start writing down some information, okay? All right. So, anybody want to say, like, what do we have first? Like, what do you guys? What are some things that they told us about here that maybe is helpful? Anything?
we got mass of the water and the copper, and we've also got temperature of the copper.
Yes, that is true. So we have, let me go ahead and put out some text box here. So let's get some knowns up here. So we were given the mass of the copper tank. So let's do knowns. Let's write this in here. And I'm going to make this a little smaller because got a lot of things to cover here. So we have mass. I'm going to put MC. So MC, mass of the copper, is equal to 13 kilograms, right? We have the mass of the water. So MW is equal to 4 kilograms, right? Just moving right along. And it says an electrical resistor of negligible mass. So we're going to assume that the resistor means essentially nothing to the total mass of the system, right? It's just very small, while the rest of it weighs quite a bit, right? 13 kilograms and 4 kilograms is a lot more than probably what that resistor weighs, so it's just a little bit negligible. All right, and it says the system is insulated on its outer surface. So what does that mean? Anybody?
No loss of heat from the system.
Yes, so it's saying that no heat is leaving the system. So Q out, I'm going to say, is, I'm pretty sure it just means Q is equal to 0, but I was going to be more specific and say heat leaving is 0. But Q is equal to 0, right? So no heat transfer leaving. And it says, initially, the temperature of the water, or the copper, sorry, temperature of the copper is 27 C. So I'm going to go over here a little bit and start talking a little bit more about the copper. So T1 copper, so T1C is copper, is 27 C. Okay? And then we have initially the temperature of the water. So we have T1 water is equal to 50 C. All right? And then it says the electrical resistor. So I'll move this one down here. So then we have the electrical resistor transfers 100 kilojoules of energy to the system. So how will we denote what the resistor is doing? What is the resistor doing exactly? Is it work? Is it heat?
We got Q in.
This one, so in this class, generally speaking, resistors are generally done as work, because we are having to make, this power is coming from somewhere, right? This electricity is coming from somewhere. So generally it is shown as work in this class. But you're right. Essentially there is heat being thrown in here, right? We can all agree on that. But usually this is the designation between work, right? Work is like something like a resistor, a paddle wheel, things like that. So we always call this one as work. So I'm going to call it work as, now what direction would it be? Is this positive work, negative work? Anybody?
It's work on
Okay.
the system, so it'd be negative.
Yes, that is correct. So it is work on the system. So 100 kilojoules on the system, okay? And then it says eventually the system comes to equilibrium. So what that right there is telling you, and now we haven't talked about this, but what that is telling you is that when it becomes equilibrium, what does that mean? That means that one side's heat transfer is equal to the other, correct? Would you guys agree? That that's what equilibrium means? That they are both in perfect balance, perfect harmony.
Yeah. Yeah, so that would be like TC, it would like be like T2C would be equal to T2W, right?
Yes, essentially they are both. Well, okay. So essentially, what we're saying is that the equation. They have given you a hint. The hint there is that there is an equation being used, and the equation being used is that you can set one side equal to the other, right? Because water, the heat transfer from water or to the water has to be equal to the copper tank's heat transfer to the water. Because there's no heat transfer leaving, right? We've already said that insulation has made that 0. So any heat transfer inside of here has to go from one and be taken away from the other. So we know that we can set it equal to each other, and we know at one point they will be in equilibrium. So that is some things that we have here. And I have... Yeah, I think this is about everything I need to write down. And the thing we're trying to find is the final equilibrium temperature and in degrees C. Okay? So if that is clear, so I'm gonna do find T2, right? So temperature 2, I'm just going to write that. So these are our knowns for the question, right? Is everybody all good on that so far? No questions, hopefully. So, really quickly, how should we approach this, right? How should we approach this? What kind of equations can we write down here? So, here I'll start here. I'll start writing something, and you guys tell me if this is intelligent or not. So, right here, let's write Q minus W is equal to U2 minus U1, right? Does this equation help us at all? This is the very base equation, by the way. This is it may not exactly fit us, but base energy balance. So this is the base energy balance for us. Does this help us? The answer is yes, it does help us. And the reason why it helps us is that we are trying to figure out how we can relate one thing to another, right? And so, right here, Q is gone, right? We can say that Q is gone because Q is equal to 0 for this. So let's go ahead and put negative work, so minus W is equal to, I wish I had a button for sum, but it's the summation of the change of energy here. It's not just U2. I guess it is U2 minus U1 in a sense, but essentially I'm going to write as U2 minus U1. But be careful here. So essentially our work is equal to the change of energy from state 1 to state 2, right? Now inside of this U2 minus U1, there are a couple of things, right? There is water, and then there's the copper, right? So we need to add something here. There's a little bit of something missing. So how we're going to do that is really fast. These are another way we're going to write this. So let's do U1C minus U2C, and I'll put this in parentheses. And I'll actually keep the equation in the same side because that would probably annoy people. Plus U1 water minus U2 water, right? Because while I agree that they are transferring energy back and forth more or less, like throughout, like one's giving energy, one's taking it away, right? And so this right here is the total energy change, right? Would you guys agree that the work has to be equal to how much energy the copper changed plus how much energy the water changed, right? In some way. Would you guys would agree with that? We're trying to hold on to all the energy, right? It's an energy balance. Everything in here has to be accounted for. And so far it is, right? So let's move down another step here. So, really quickly, how can we show energy change? Remember, we just talked about this. How can we show energy change? And I think someone in here brought it up just a minute ago. It might have been Tanner or Michael. You guys brought this, one of you brought it up just a minute ago. How can we relate energy change when the only things we know are temperatures? We just talked about how we can do this.
You need a specific heat.
Correct. So this is a specific heat question. So another surefire way to tell if there's a specific heat question is if they give you, the only thing they give you is masses and temperatures. Because if there are no pressures, there is no way you guys can really figure out much about this. Now, okay, I can agree you can find it for water, right? Because if it's liquid water, which, although really quickly, you can't actually tell that, although it tells you it's liquid water, so we actually can know. But if they didn't tell you it was liquid water, there's no way you could know what state it was because they didn't give you any other ways to find it. So, but the liquid water gave it away that it is liquid, therefore it's saturated liquid, right? Whereas we assume it's a saturated liquid because we just said, remember, if it's liquid water, we use the liquid water values to approximate at a temperature, correct? So we just talked about that, the approximation of it. So that's right there, liquid water. When you see something like that, that is another hint. Another hint meaning that it is liquid water, and you use the liquid water table at the temperature, not the pressure. Okay? So that was another hint in a lot of ways. But, yes, for this one we need specific heats. Okay? So, how we're going to do this is we have to go and find the specific heats, right? Because I'm going to go ahead and write the equation in the way that Tanner, I think, said. So, really quickly, this is what he's saying. The equation for specific heats are m dot c. So, it's m. So, if you want this in terms of total energies, you have to multiply by a mass, right? And our work is in kilojoules, so we need it to be multiplied by a mass. So, mc times Cp of C. So this is the mass of the copper times the specific heat of copper times, so I'll do this again, times T1 copper minus T2 copper, right? Does that make sense? So this right here is this equation right here, this MCP delta T is what it's actually referred to as MCP delta T. It is the exact same thing as this U1 minus U2. You will get the same answer. Or it's a close approximation. They should be very close. And so this right here is the same as that. It's a replacement, a direct replacement. Now, we have the following. We have to do the water one, right? So really quickly, you have MW times CPW times, let's make this a little longer, T2W minus T1W. So the reason why I changed that, I flipped those around, is because I know the heat. So I think the heat transfer, one sec. So the water's heat transfer is negative, so this should be the other way, I think. Let me make sure I get this right. So the water's heat transfer is negative, right? Because water is losing heat to the copper. Because it's initially at 50, it's the higher of them, so it's going the other way. So the reason why you want to try and keep track of this is that at the end you might get an answer that doesn't make sense. And by the way, I often do this. I often get an answer at the end that like doesn't make sense doing this calculation, and you have to be a little bit smart and figure out, that doesn't make sense. Like, how could I have gotten an answer higher than the initial temperature or lower than the initial temperature? It's impossible. So you have to make sure you keep the track of these, right? And kind of think to yourself, what makes sense for this? This is a question I commonly get wrong. Not wrong because I figure it out afterward, but I always figure out because I mess up these two locations in here, the T2 and T1 thing. All right, so now that we have that, there are some things that we need, right? So I'm going to go ahead and click that off. This is what we're dealing with. So this is, once again, MCP delta T for both water and for copper, okay? What we need to do is we need to go find the CP for copper and the CP for water, right? We have everything else here except for, obviously, T2C. And really quickly, T2C and T2 water are the exact same temperature because we made it to equilibrium, right? I think somebody mentioned that earlier. I don't know who it was, but somebody mentioned that we were in equilibrium at the end, and therefore our temperature at the final state is the same, right? So T2C and T2 water are the same, but I like to split them up, and the reason is because in some of these questions, they are not the same. In some questions, T2 water will be different than T2 copper because I think the question is worded differently. And it doesn't, I think it's like encased in something. It's not actually touching. They're not contacting in some way. So it ends up being that they're different. So I like to split them up. But just to not confuse you, I will write that out. So for this question specifically, T2 water is equal to T2 of the copper, right? Just because we are in equilibrium at the end. So now, how do we do this? Well, we go to our handy dandy tables. And so we need to find the specific heats of water, right? So here's the problem is that that one that I showed you earlier was only gases, right? It was nitrogen, oxygen, air, right? That's not going to help us here. What we need is this one. I believe table A19, it says properties of selected liquids and solids, CP, rho, and K. So we're going to go try there first. And really quickly, this is the first page of the table, so you can see what all of them are, right? And so this would be somewhere you would go first to find things. So let's move, let's go to table A19, which is on 960. But I don't have that one, actually. I can't just jump to that because I only have the tables. Let's see, I think that's not it, is it? Yeah, here it is. So, is water in here? Here it is. So, here's water, right? And here's the CP of water, density and thermoconductivity. So let's go down this one right here. So water at 275 Kelvin. Our temperature of water starts out at 50, correct? So how you generally want to do these is that you generally want to... So a lot of times in heat transfers, you pick a middle of the road specific heat. The problem is that because we don't know where they're going to end, you can't do that. So we're going to have to just pick them from right here at the starting point. Like an average specific heat, but now we can't. So I'm going to go find, so we have 50 plus 273. It gets us to 323. So we're going to go ahead and take 325 Kelvin. So I changed our temperature. So really quickly, I changed our temperature of the water to Kelvin, which if you add 273, you end up getting it. And it ends up to be 323. So we're just going to take 325. So 4.182 is our specific heat of water, okay? So let me go ahead and pull that back out over here. So I'm going to put it in the knowns column here. So CP water is equal to 4.182. And this is in kilojoules per kilomole, I think. I don't know which one they have it listed as, actually. Let me be sure before I write that down. This is in kilojoules per kilogram Kelvin. Got it. Kilojoules per kilogram K. All right. And now we have to find the CP of copper, right? Next one over. And let's go back over to the table. So copper is right here. And the specific heat of copper, it does not list it as changing at anyone. This is selected solids at 300 Kelvin, so, you know, near room temperature, I guess. Actually, room temperature is at 300 Kelvin. It's 293, I think. But anyway, whatever. 0.385 kilojoules per kilogram Kelvin is our one for that as well. So let's go ahead and bring that in as well. So 0.385, I think, is what it was. I have a tendency to gloss over that, but who knows? Let me go back and be sure. 0.385. So this right here is where we get our specific heats. So now that we have those, right? Now that we have our specific heats right here, we can fill out this question, right? Pretty straightforward from here. It's just it's a manipulation of the variables at hand. So I'm going to go ahead and maybe do this by hand, although we'll see. Essentially, you have to do some math here, right? You're going to have to manipulate this around in front of you. I actually have the answer, so I know what the final equation is. But essentially, just how you're going to have to do this is you're going to have to multiply in, distribute the MCPs to both of these both of these two. You distribute them in, and then you're going to separate the T1s and the T2s, because remember, T2 of water and copper are the exact same thing. So that's something I'm about to do. I'll just change the equation to include that, because that's going to be confusing. I should have just done it from the beginning. T2 minus T1C plus MW times CPW times T1 water minus T2. Okay? So essentially, I just replaced that there's no T2C or T2W. So what you're going to do is, like I said, you multiply in and you distribute these two into here. And you get all the terms essentially by themselves multiplied by MW MCP, and then you get the T2s by themselves, and you move the work over as well, because remember the work is still here. It is still on this side, so we do have to include it. So the final equation, which obviously me doing this by hand on a computer is kind of hard to do. If I write it out, it looks really bad. So I'm going to just show you what the final equation looks like. It looks like the following. So T2 is equal to MC, so this is the mass of copper, right, times the CP of copper times T copper 1. So essentially TC1 or T1C, that's what I had, T1C, right? And then it's plus the mass of the water times the CP of water times the T1 water minus the work. So let's put W there. And then it's divided by, this stuff's on the bottom, is MC times CPW. Or no, times CPC, that's right, CPC. And then it's plus MW times CPW. So this is what it looks like. This is once you do this manipulation, you should get this right here. And if you fill in your numbers here, which now there is one trick to this, right? There's a trick here. So really quickly, you do have to be careful because these temperatures have to be in Kelvin. Because remember, your units have to work out. So for example, remember CPW here needs to be absolute, right? Because remember, this is kilojoules per kilogram and Kelvin, right? So you do have to be careful that these are in the correct units. So you have to change your temperatures to Kelvin. So temperatures have to go to Kelvin, but besides that, it all works out. But there is one last one here that is a pitfall for a lot of people. Right here is the work. So make sure we watch the sign here, because inside, so we have minus W, which is minus, because remember, our work is already negative because it's a work going in. So this becomes a positive. Essentially, you're going to add 100 kilojoules here. And what would have happened if you flipped that is that essentially what that means is that if you flip this sign and you just subtract the work, what that means is, essentially, is that work is leaving. So energy is leaving in the form of work. So you're subtracting off work, leaving the system, and it would have your final temperature be lower than it should have been. So you do have to be careful, okay? You just have to make sure you have to know which way the work is going and then place it inside of there. And like I said, you would have gotten a lower temperature had you done that. You would have gotten, I don't know what you would have gotten, but it would have been lower than the correct answer. Because remember, this whole equation right here is just an energy balance. And so what that means is that it's taking all of the energy together and it's figuring out what the final temperature was using that energy. How did we raise the temperature? How did we lower the temperature? And work is a part of that energy, right? Work is a part of it. And if it leaves, it affects the temperature. If it enters, it affects the temperature, right? So we have to be sure we know the direction here, or else, all hell breaks loose. So, really quickly, just so we can get some closure onto this question, if you plug in all of your numbers here, and I know this is kind of an annoying thing to plug in, maybe your calculator can do it, I don't know, but essentially this is something that you should expect to know on an exam, because this question isn't really that hard, right? Like, this question wasn't really that hard, it's just you have to know this little balance and all of that, right? It's not a very difficult question. The final answer here, when you do all of that, you end up getting a temperature of 322 Kelvin, 0.3 Kelvin, which ends up being 49.3 Celsius. That's what you end up getting as the final answer. This is the final answer of the question. So, what that means is that the copper's temperature got raised really high, right? It went way up. And the water's temperature didn't drop very much at all, right? It only went down by 0.7 degrees C, right? At least I believe that's how it was. Yeah. So this right here is a very typical question that you can find yourself doing on an exam, and probably on your homework. I'm pretty sure your homework, not this one coming up maybe, I'd have to look, but I'm fairly certain that you will have to do a question like this. Maybe someone in here knows if your homework has this or not. A question like this. But I don't think so. I'll look at homework 4 real fast and see if it does. Yep, it does. So homework 4 has a question there. Homework 4 has a question right here. In a heat treating process, a 1 kilogram metal part initially at this is quenched in a tank containing water, right? And it gives you the specific heats right here. So this is a question. Determine the final equilibrium temperature. So right here, I have just showed you how to do that question. This is it right here. So don't forget this. This is essentially that question, except you're just gonna do it. Maybe there's heat transfer coming in, or there's no work or heat transfer, right? You could just set one side equal to the other. You see? So you just have to see. This right here is the process for how you should do basically every question in this class. Is what we've done here, and you guys followed along really well. And you guys had a good attitude. You go through the question and you just pick these things out. And then you just let these be the guide, and just move through like this. Just take little things, write down the equations, and eventually it turns into something that is an answer, right? But I'm going to go ahead and take attendance really fast. I'm going to stop the old video, and you guys will be free to go.